On the 24th of October, 2003, the most advanced civil airliner ever built made its final approach into Heathrow. It touched down at 16:05. The crowd on the observation deck numbered in the thousands. Some wept openly. The aircraft that had crossed the Atlantic in 3 hours and 28 minutes less time than it takes to drive from London to Edinburgh was being retired. Not because it was worn out, not because something faster had replaced it, because it could not pay its way. That aircraft was Concorde. It cruised at Mach 2.04, twice the speed of sound at 60,000 feet, where the sky above turns from blue to black and the curvature of the Earth is visible through the flight deck windows. Its passengers arrived in New York before they had, by the clock on the wall, left London. No civil aircraft before or since has matched it. And yet the production line had closed 30 years earlier, after just 14 aircraft were delivered. Every airline that had placed an order, Pan Am, Tobibue, Japan Airlines Lufthansa, and 16 others, had cancelled. The two operators who flew it, commercially British Airways and Air France, had received their aircraft at a price that covered neither development nor production costs. The bill for building Concorde, borne entirely by British and French taxpayers, ran to approximately £1.5 billion by 1976, equivalent to roughly £12 billion today. Not £1 of it was recovered, but the real story of Concorde is not the spectacle of its retirement, nor the long shadow of its balance sheet. It is the story of what happens when two governments sign a treaty with no exit clause, when engineers are asked to solve a problem that politics has already made unsolvable, and when national prestige is placed ahead of commercial reality and held there for 40 years at twice the speed of sound. In November 1956, the Supersonic Transport Aircraft Committee, known within Whitehall as STAC, convened for the first time at the Royal Aircraft Establishment in Farnborough, Hampshire. Its membership, drawn from the Ministry of Aviation, the aircraft industry, and the nation's leading aeronautical research institutions, the committee had been given a single remit to determine whether a supersonic civil transport was technically feasible and whether Britain should build one. The Cold War was 3 years past its first hydrogen bomb tests. The jet age had arrived with the de Havilland Comet. The question now was what came next. The strategic logic was clear enough. Britain's aircraft industry in 1956 was still one of the finest in the world, scarred by post-war contraction, yes, but capable of producing world-leading designs. The de Havilland Comet had been the first jet airliner in commercial service anywhere on Earth, entering service with BOAC in May 1952. The catastrophic metal fatigue failures that grounded it in 1954 had been a humiliation, but the engineering lessons extracted from those crashes had advanced the understanding of high-altitude flight further than a decade of peacetime research might have managed. Britain had knowledge. It had facilities. It had at Farnborough and at Bristol the aerodynamic expertise to attempt something that no nation had yet achieved in civil aviation. Stas's final report, delivered in March 1959, concluded that two viable supersonic transport designs were achievable: a medium-range aircraft capable of Mach 1.2 and a long-range transatlantic design capable of Mach 1.8 to 2.0. The long-range variant was the one that mattered. The North Atlantic route, London to New York, was the most commercially valuable air corridor on Earth. If a supersonic aircraft could be made to fly it in under 4 hours, the market in theory was enormous. The British aircraft industry's response came primarily from two directions. At Bristol Aeroplane Company in Filton, a design team under the chief engineer Archibald Russell had been developing supersonic transport concepts since the early 1950s. Russell was one of the most experienced aerodynamicists in Britain, a veteran of wartime bomber design who had spent the post-war years studying the behavior of wings at transonic and supersonic speeds. At the same time, Hawker Siddeley's division at Hatfield was pursuing a parallel study. The two approaches differed significantly in their treatment of the wing, the single most difficult engineering problem in the entire program. At supersonic speeds, a conventional swept wing generates enormous drag and becomes aerodynamically unstable. Russell's team at Bristol concluded that the solution lay in a slender delta configuration, a long, thin triangular wing with a sharply curved leading edge technically described as an ogival delta. At low speeds, this wing is aerodynamically inefficient. It generates lift only through a controlled vortex that forms along its leading edge, requiring the aircraft to fly at a high angle of attack on approach nose pitched up the flight deck, effectively blind to the runway ahead. The design demanded either a drooping nose, a section of the fuselage forward of the flight deck that could be lowered for takeoff and landing, or an entirely novel approach to pilot visibility. Russell's team chose the droop nose. It was an inelegant solution to an unavoidable problem, and it would become one of Concorde's most recognizable features. The competition for the British design contract effectively resolved itself before a formal tender was issued. Bristol's accumulated research depth, its existing wind tunnel data, and Russell's team gave it an insurmountable advantage over Hawker Siddeley's parallel study. By 1961, Bristol, soon to be absorbed into the British Aircraft Corporation under the government-directed consolidation of the British aerospace industry, held the dominant position on the British side of what was becoming an international program. Because by 1960 it had become apparent to the Ministry of Aviation that Britain could not afford to develop a supersonic transport alone. The development cost estimate, even at this early stage, was running at £150 to £170 million. In 1960 values. The ministry began looking across the channel. France had reached the same conclusion from the opposite direction. Sud Aviation in Toulouse, working under chief designer Lucien Cervanti, had developed a supersonic transport concept, the Super Caravelle, that bore striking similarities to Bristol's slender Delta approach. Both teams had arrived at roughly the same aerodynamic solution independently. The overlap was enough to make a joint program viable. The political appetite in both London and Paris, both governments anxious to demonstrate post-war industrial relevance on the world stage, made it desirable. On November the 29th, 1962, the British and French governments signed a treaty in London, committing both nations to the joint development and production of a supersonic civil transport. The agreement allocated development costs equally between the two countries. It specified no upper limit on expenditure, and it contained no withdrawal clause. Either government could theoretically walk away, but only by breaching an international treaty and absorbing the full diplomatic and financial consequences of doing so. It was, as one senior ministry official later noted in a memorandum now held in the National Archives' Avia series, a commitment with no visible exit. The initial development contract was valued at £150 million to be shared equally. It would not remain at that figure for long. The aircraft that emerged from Bristol and Toulouse over the following decade was by any engineering measure extraordinary. Concorde was 194 feet long, longer than the Wright brothers' entire first flight. Its ogival delta wing spanned 84 feet. Fully loaded, it weighed 408,000 pounds at takeoff, yet it was built primarily from aluminium, not the titanium or steel that American engineers had concluded were necessary for sustained supersonic flight. That conclusion, it turned out, was wrong, and the reason it was wrong tells you everything about what Concorde's engineers actually achieved. At Mach 2, the friction between an aircraft's skin and the atmosphere generates significant heat, a phenomenon known as kinetic heating. At the speeds Concorde was designed to sustain, the skin temperature on the leading edges reaches approximately 127 degrees Celsius. On the nose, it reaches 153 degrees. The American supersonic transport program, the Boeing 2707, which was pursuing Mach 2.7, concluded that these temperatures ruled out aluminium entirely and mandated a titanium airframe, driving costs to levels that ultimately killed the program when the U.S. Congress cancelled it in 1971. The Bristol and Toulouse teams reached a different conclusion. At Mach 2.0, 4, not Mach 2.7, a specially formulated aluminium-copper alloy, designated RR58, could sustain the thermal loads across a standard transatlantic sector. The choice of Mach 2.04 was not arbitrary. It was the precise speed at which the most capable aluminium alloy available could be made to work indefinitely without fatigue failure. The entire aircraft was in a sense designed around the thermal limit of a metal. The consequences of that decision ran through every system on board. Concorde's fuselage expanded by as much as 10 inches in flight as the aluminium heated and stretched engineers left deliberate gaps in the airframe to accommodate it. The fuel was used not merely as propellant, but as a heat sink circulated through the airframe to absorb and redistribute thermal energy before being burned. The flight engineer's panel Concorde retained a 3-crew flight deck, long after 2-crew operation had become standard on subsonic jets. Included a fuel transfer system of considerable complexity used to shift weight between fore and aft tanks to maintain the aircraft's center of gravity as it accelerated through the sound barrier and the center of lift shifted rearward. Managing that shift automatically was beyond the avionics of the era. The flight engineer managed it by hand, transferring fuel in precise sequences on every flight. The engines were equally remarkable. 4. Rolls-Royce/Snecma Olympus. 5 9.3 turbojets, each producing 38,000 pounds of thrust with reheat. Engage drove Concorde to its cruising speed. The Olympus had begun its life as the power plant of the Avro Vulcan, the RAF's nuclear deterrent bomber, where it had proven itself one of the most reliable jet engines in British service. For Concorde, it was redesigned from the ground up for sustained supersonic cruise operating at temperatures and pressure ratios that would have destroyed any contemporary turbofan. It remains to this day the most thermally efficient jet engine ever fitted to a civil aircraft. The test program was extensive and, by the standards of the era, rigorous. The first British prototype, designated 002, built at Filton, made its maiden flight on 9th April 1969, piloted by Brian Trubshaw, BAC's chief test pilot, with co-pilot John Cochrane. The French prototype, 001, had flown first on March 2, 1969, from Toulouse, with André Turcat at the controls. Testing was conducted across 3 continents: at Fairford in Gloucestershire, at Cassaux in France, at tropical trial sites in Nairobi and Bahrain, and at the A&AEE at Boscombe, down in Wiltshire, where the aircraft's handling qualities and systems were subjected to the full battery of British military airworthiness evaluation. 5,000 hours of flight testing were accumulated before the Certificate of Airworthiness was issued in September 1975. What broke first was not the airframe nor the engines. It was the brakes. Concorde's landing speed, approximately 187 miles per hour, was 40 miles per hour faster than any contemporary airliner. The carbon brake technology required to arrest that mass at that speed did not yet exist in a form suitable for airline operations. Dunlop's aviation division spent 3 years developing a carbon composite brake assembly specifically for Concorde, a program that generated patents still in use on high-performance aircraft today. The political case for the program was sustained throughout the test period by a combination of performance margins and industrial leverage that no competing design could match. By the time the production aircraft was flying, Bristol's design team, now operating within British Aircraft Corporation, had accumulated 4,000 employees at Filton alone, working directly on the Concorde program. A further 6,000 jobs across the southwest of England, the Midlands and Scotland depended on Concorde subcontracts. Rolls-Royce at Derby employed 1,800 engineers on the Olympus 593 program. The economic geography of British aerospace had been reorganized around this aircraft. Cancelling it, as the Heath government briefly contemplated in 1973, would have devastated communities from Bristol to Glasgow. The decision was made. The program had its champion not in any single minister, but in the weight of industrial dependency that made cancellation politically unthinkable, even as the commercial case continued to deteriorate. British Airways, formed in 1974 from the merger of BOAC and British European Airways, took delivery of its first production, Concorde Dubuis, in January 1976. Air France received its first aircraft the same month. Commercial service began on January the 21st. 1976. British Airways flew London Heathrow to Bahrain, Air France flew Paris to Rio de Janeiro. The North Atlantic route, the route the entire program had been built to serve, did not open until November the 22nd, 1976, following a protracted legal and political battle with the United States government over landing rights at John F. Kennedy International Airport. That battle, and the reason it was so difficult to win, would prove to be the first public confirmation of something the engineers had known since 1961. 20 production aircraft were built in total, 14 delivered to airlines, 6 retained as development and pre-production airframes. British Airways operated 7. Air France operated 7. No other airline ever took delivery of a single aircraft. Of the options placed by Pan American, TWA, Japan Airlines, Lufthansa, American Airlines, United Air Canada, Braniff, International Continental, and a further 9 carriers between 1963 and 1972. 74 options in total, representing a commercially viable program. Everyone was cancelled before the first production aircraft flew. The reasons were multiple and compounding. The 1973 oil crisis had quadrupled fuel prices, and Concorde's fuel consumption per passenger was approximately 4 times that of a Boeing 747. Environmental pressure groups had begun lobbying against supersonic aviation on noise grounds. And beneath both of those pressures lay the fact that had been present from the beginning, unresolved, unresolvable, and now impossible to ignore: the sonic boom. At supersonic speeds, an aircraft generates a continuous pressure wave, a sonic boom that propagates across a corridor approximately 50 miles wide along its entire flight path. On the ground, it arrives as a sharp double crack, loud enough to shatter windows at low altitude, audible and disruptive at cruise altitude. In April and May of 1964, the United States Federal Aviation Administration had conducted a systematic test program over Oklahoma City. 90 supersonic passes over 8 months, affecting 50,000 residents, to determine public tolerance for sonic boom exposure. The results were unambiguous. Residents filed 15,000 formal complaints. The program was abandoned. In 1973, the FAA banned all civil supersonic flight over the continental United States. The same restrictions followed across most of the world's major landmasses. Concorde had been designed for a world in which supersonic flight was permitted everywhere. It was now confined to oceanic routes, principally the North Atlantic, where the boom fell on water. The aircraft that was supposed to transform intercontinental aviation had been legislated into a single corridor between 2 cities. Everything that followed the commercial record, the financial arrangements, the ultimate withdrawal, flows from that single regulatory fact. Within those constraints, however, what British Airways and Air France built was genuinely remarkable. The transatlantic service that opened on November the 22nd, 1976. London Heathrow to John F. Kennedy, operated by British Airways as Speedbird Concorde, set a standard of speed and consistency that no civil aircraft has matched before or since. The scheduled block time was 3 hours and 30 minutes westbound, 3 hours and 50 minutes eastbound against the prevailing winds. The actual fastest recorded transatlantic crossing by a British Airways Concorde was 2 hours, 52 minutes and 59 seconds, set on 7th of February, 1996, aided by the jet stream. New York to London in under 3 hours. The sun rose twice on the same morning for passengers who crossed the Atlantic eastbound and overtook it. At peak operation in the mid-1980s, British Airways was flying 5 daily Concorde departures from Heathrow to New York, JFK to New York, Newark to Washington, Dulles to Miami, and seasonal services to Barbados and to Singapore in partnership with Singapore Airlines. The Singapore service operating the London-Bahrain-Singapore routing was the only regular Concorde operation east of the Gulf, a route that required special overflight agreements with no fewer than 11 sovereign states and demonstrated the aircraft's operational reach when diplomatic groundwork was done correctly. The passenger experience was calibrated to a specific market: senior corporate executives, heads of state, entertainment figures, and individuals for whom time was measurable in thousands of pounds per hour. A return transatlantic fare on Concorde in the late 1980s cost approximately £6,000, roughly £18,000 in today's values. The cabin held 100 passengers in a single class in seats narrower than contemporary business class, but in a fuselage pressurized to the equivalent of 6,000 feet lower than any subsonic airliner, giving passengers an arrival experience notably free of the fatigue associated with a long-haul flight. The windows were small, barely larger than a paperback book. Because at 60,000 feet, the differential pressure loads on a larger aperture would have demanded structural reinforcement that the weight budget could not absorb. The crews were drawn from British Airways' most experienced pilots. A Concorde command required a minimum of 7,000 hours on type and a conversion course that emphasized the fundamental difference in energy management between subsonic and supersonic flight at Mach 2. The aircraft cannot simply throttle back and descend. The deceleration profile from cruise to approach required a carefully managed sequence beginning 300 miles from the destination. The pilots who flew it consistently described it as the most demanding and most satisfying aircraft they had operated. Captain John Hutchinson, one of British Airways' senior Concorde commanders, noted that the aircraft required its crew to think at least 200 miles ahead of the airframe at all times. Rolls-Royce's Olympus 593 engines delivered a dispatch reliability rate of 99.6% across British Airways' operational life, a figure that put the engine among the most reliable power plants in commercial aviation history. Each engine underwent a major overhaul every 1,200 flying hours, frequent by subsonic standards, but a function of the extreme operating temperatures rather than any fundamental unreliability. The engines were maintained at Heathrow's dedicated Concorde facility, a purpose-built maintenance complex that employed 400 technicians whose entire professional expertise was specific to this one aircraft type. Commercially, the picture was more complicated. For the first 2 years of transatlantic operation, load factors were poor. The aircraft flew routes that were politically won, rather than commercially optimal. And the oil crisis had made operating costs almost impossible to project with confidence. In 1979, British Airways restructured its Concorde operation under a new financial framework. Negotiated with the government, the aircraft's capital costs, development and production were written off entirely by the state. British Airways would pay only operating costs and a nominal lease on each airframe. Under that arrangement, and only under that arrangement, Concorde became profitable. By the mid-1980s, the transatlantic service was generating an operating surplus of approximately £30 million per year for British Airways, a figure that management cited frequently and that obscured just as frequently the several billion pounds of taxpayer capital that had made those profits structurally possible. The first signs of institutional strain emerged not from the aircraft, but from the world around it. The deregulation of transatlantic aviation through the late 1970s and 1980s brought new competition and collapsing subsonic fares. Business class on a Boeing 747 was becoming fast enough, comfortable enough, and cheap enough to begin eroding the argument for paying a Concorde premium. Airbus's twin-aisle, wide-body fleet was modernizing the subsonic long-haul experience in ways that reduced the perceived gap between supersonic and conventional travel. The Public Accounts Committee, in a 1984 report, noted pointedly that Concorde's apparent profitability depended entirely on a financial structure that no normal commercial operation would have survived, and questioned whether the operating surplus justified continued government support for maintenance and infrastructure costs not included in British Airways calculations. The program was not in crisis, but the margin was thinner than the headline suggested, and the aircraft was aging. By the early 1990s, the youngest production Concorde was already 15 years old. The fleet had no replacement. No government on either side of the channel was prepared to fund a successor. The supersonic era, it was becoming clear, was not a beginning. It had been an interlude. On 25th July 2000, Air France Flight 4590 departed Charles de Gaulle Airport at 1642 local time. It was a charter service bound for New York, carrying 100 passengers and 9 crew. 97 seconds after brake release, the aircraft struck a titanium alloy strip that had fallen from the engine cowling of a Continental Airlines DC-10 that had used the same runway minutes earlier. The strip lacerated a tire on Concorde's left main undercarriage. A fragment of rubber traveling at enormous velocity struck the underside of the left-wing fuel tank with sufficient force to generate a hydraulic pressure wave that ruptured the tank from within. Burning fuel streamed from the wing. The engines lost power asymmetrically. The aircraft, already committed to takeoff speed and unable to stop within the remaining runway, became airborne in an uncontrollable condition. It crashed into a hotel at Gonesse 4 minutes after leaving the runway. All 109 people on board were killed, along with 4 on the ground. The cause was not a flaw in Concorde's fundamental design. The titanium strip on the runway was foreign object debris, the responsibility of the Continental Airlines maintenance team that had fitted the cowling incorrectly. The chain of events that followed, however, exposed something that had been present in the aircraft's fuel tank design for years. A vulnerability to tank rupture from external impact that British and French airworthiness authorities had identified in earlier safety reviews, but had not mandated as a priority modification. That detail would matter enormously in the months that followed. The certificate of airworthiness for all Concorde aircraft was suspended by the French Direction Générale de l'Aviation Civile on August 16, 2000. The British Civil Aviation Authority followed the same day. For the first time in 24 years of commercial operation, Concorde was grounded. Both British Airways and Air France announced immediate suspension of all services. The modification program that followed Kevlar lining for the fuel tanks redesigned electrical wiring new tire design to reduce fragmentation risk cost. British Airways approximately £17 million per aircraft. Concorde returned to transatlantic service on 7th November 2001 to considerable public celebration and media coverage that emphasized the aircraft's resilience and the thoroughness of the modifications. What the coverage did not emphasize was that the aircraft had returned to a world that had fundamentally changed. On the 11th of September 2001, 35 days before Concorde resumed service, the destruction of the World Trade Center had collapsed transatlantic business travel demand by approximately 30%. The corporate executives and senior business figures who comprised Concorde's entire passenger base were flying less flying subsonic when they did fly, and doing so under pressure from boards and shareholders newly sensitive to executive travel expenditure. The load factors on Concorde's resumed services were, by the standards of the pre-crash era, poor. The operating surplus that had made the aircraft commercially defensible had evaporated. Air France moved first. On April 10, 2003, Air France announced that it would retire its Concorde fleet on May 31, 2003. The stated reason was the aircraft's age and the cost of continued airworthiness maintenance. The unstated reason was simpler. Without the transatlantic business traffic that had sustained the service, the route could not generate an operating surplus sufficient to justify the program's unique and irreducible overhead costs. British Airways initially announced it would continue operating. Within weeks, Airbus, which had absorbed Aerospatiale and now held the type certificate and airworthiness support obligations for the Concorde airframe, informed British Airways that it would withdraw engineering support for the aircraft at the end of 2003. Without Airbus support continued, airworthiness certification was not possible. British Airways had no choice. Then the pace accelerated. The announcement came on April 10, 2003. Both airlines same day. Airbus support withdrawn. No successor aircraft existed. No government was willing to fund one. The transatlantic market had moved on. The economics had never worked. The political will that had sustained the program for 40 years had finally exhausted itself. Meetings were held. Letters were written. The last scheduled service was confirmed for October. No new orders came. No government intervened. No white knight appeared. Filton began winding down its Concorde support contracts in June. Heathrow's dedicated maintenance facility began preparing its final technical records. Rolls-Royce closed the Olympus 593 parts supply program. The last revenue flight departed New York, JFK, on the 24th of October 2003. British Airways Concorde G-BOSG call sign, Speedbird Concorde. One landed at Heathrow at 16:01. Two further aircraft G-BOAE and G-BOAB landed in close succession, completing a final three-aircraft formation approach that the airline had arranged for the occasion. The runway cameras caught them on finals together. The crowds on the observation deck were already there. The certificate was surrendered. The type was retired. The line was closed. 20 aircraft built, 14 delivered. 2 operators, 1 route that mattered. 31 years from treaty to retirement. Total development and production cost to the British taxpayer approximately £1.5 billion at 1976 values. Revenue recovered from that investment? None. The silence on the North Atlantic from 25th October 2003 was not dramatic, it was simply permanent. Concorde did not disappear cleanly. It left traces in wind tunnels, in design offices, in the careers of engineers who had spent their working lives solving problems that no other program had ever posed. Those traces are still visible if you know where to look. The Ogilvy Delta wing that Archibald Russell's team developed at Filton in the late 1950s became the foundational aerodynamic reference for an entire generation of European high-speed research. The computational fluid dynamics tools developed to model Concorde's complex vortex lift characteristics were directly inherited by the Airbus A300 and A310 wing design teams at Hatfield and Bristol. The thermal management techniques pioneered for the RR-58 aluminium alloy airframe using fuel as a distributed heat sink managing skin expansion through deliberate structural tolerance informed the materials engineering approach taken on the Eurofighter Typhoon's predecessor studies at British Aerospace through the 1980s. The carbon composite brake technology developed by Dunlop specifically for Concorde's high-energy landing requirements is now standard across the commercial aviation industry. Every wide-body airliner that lands at Heathrow today stops on technology that Concorde made necessary. The Olympus 593's influence runs deeper still. The engine's core thermodynamic cycle operating at pressure ratios and turbine entry temperatures that were in 1965 considered by several senior Rolls-Royce engineers to be physically unachievable established a performance benchmark that accelerated the development of the RB211 high-bypass turbofan. The materials science required to keep the Olympus 593 intact at those temperatures drove advances in turbine blade cooling and nickel superalloy processing that fed directly into every subsequent Rolls-Royce military and civil engine program. The engineers who solved the Olympus 593's thermal problems went on to solve the RB211's fan blade problems. The knowledge transferred in people, not in documents. Archibald Russell himself retired from British Aircraft Corporation in 1969, the year Concorde first flew, having spent nearly 4 decades in British aeronautical engineering. He was appointed a Commander of the Order of the British Empire, a CBE, in the 1970 New Year Honours list. In retirement, he remained a visiting fellow at Bristol University's Department of Aerospace Engineering, where he continued to supervise postgraduate research into delta wing aerodynamics until the late 1970s. He died in 1994, 9 years before the aircraft he had conceived made its final landing. He did not live to see Concorde retired. Whether that constitutes mercy or misfortune is a question each viewer must answer for themselves. Brian Trubshaw, who had flown the British prototype on its maiden flight in April 1969 and served as BAC's Director of Flight Testing throughout the certification program, retired from flying in 1986. He wrote a memoir simply titled Concorde that remains one of the most technically precise first-hand accounts of a major civil aircraft development program in the English language. He died in March 2001, 2 years before the retirement, and 14 months after the Paris crash that had grounded the aircraft he had spent his career bringing into service. He had seen Concorde survive its worst moment. He did not see it end. The honest verdict on Concorde rendered by procurement historians and aviation economists with the benefit of 50 years of perspective, is uncomfortable but consistent. The program should not have been launched on the terms on which it was launched. The 1962 treaty, with its absence of a withdrawal clause and its absence of a cost ceiling, was an act of political commitment masquerading as an industrial agreement. The sonic boom problem was sufficiently well understood by 1961, before the treaty was signed, that a rigorous commercial assessment would have identified the oceanic route confinement as a fatal constraint on the program's economics. That assessment was not made, or if it was made, it was not allowed to influence the decision. The program proceeded because neither government was willing to be seen to have stepped back from a technological frontier, and because the aeronautical industries of both nations needed the work. What resulted was an aircraft of genuine and extraordinary capability, operated commercially for 27 years, beloved by the people who flew it, and by an entire generation who watched it overhead and felt briefly that the future had arrived on schedule. That is not nothing. It is, in fact, considerable. But it was purchased at a cost that was never honestly accounted for by governments that had committed themselves beyond the point where honest accounting was possible. Concorde was not a failure of engineering. It was a failure of governance dressed for 27 years in the most beautiful airframe that British and French hands ever built. If you found this history valuable, give the video a like. It is the single best signal you can send this channel. And if you want more stories about the aircraft, the ships, and the decisions that shaped British military and aviation power, subscribe to UK Defence Archive. We will see you in the next one. Music. On a morning in February 1996, at 60,000 feet above the North Atlantic, British Airways Concorde G-Bud accelerated through Mach 2 on the New York track, its aluminium skin stretching 10 inches in the heat of its own passage, the curvature of the Earth visible through windows the size of a paperback book. The ocean 4,000 feet below, still in darkness, while the flight deck caught the first light of a sun. The passengers had already left behind, and for 2 hours and 52 minutes, nothing built before or since went faster, flew higher, or carried the weight of a nation's ambition with more precision or more grace.